Okay, thank you. And well, I want to thank the organizers for the invitation to speak here. So I'm going to talk about some joint works with Fabio Tal from USP. And the problem that we are interested in is the following. We consider homeomorphism of a compact surface, which is area preserving, and assume that there is some topological disk, some set which is homeomorphic to an open disk in the surface, which is invariant by the dynamics. And what we want to understand is how the invariance of this disk restricts the dynamics of F, or what does it imply on the dynamics of F in the boundary of this region. So in what sense we want to understand this? Well, the idea is that we want to know how does the topology of the boundary of this open set, or the closure of this open set, restricts the dynamic. This will become clear when here's an example of the type of things that we want to consider. This open set U above spirals around the surface and accumulates on something. So the idea is, what does this have any consequence on the type of dynamics that can show up in this accumulation set? So what can we say about the dynamics in this accumulation set of U? An example of something that we don't care much about is the bottom example, where the open set is simple from the point of view of the topology of the ambient space. So it doesn't see the surface. It remains in a bounded in a disk. So another example is if you take an irrational flow in the torus and you thicken one of the orbits so that it becomes a disk which spirals around, wraps around in the torus, and then well, if this disk is invariant by some area preserving homeomorphism, what can we say about the dynamics in its boundary? The boundary of this disk is a large set. In fact, another way to obtain this same thing, the same disk, is looking at the DA map in the torus. So you start with a linear Anosov map and you make one of the a fixed sink. You turn it into a fixed saddle. You turn it into a source. Then in the complement appears an attractor, which is precisely the boundary of a disk, as in the previous picture. The black thing here is the disk which is wrapping around, which is the thickened unstable manifold of the saddle. And then the orange part is the attractor. So the question is, if this black disk is invariant by an area preserving map, what can we say about the dynamics in the orange region? So the type of, the general idea that we have is that if the topology of the boundary of the open set is complicated in some sense that we have to define properly, then the dynamics there has to be very simple. So here is an example of something which we consider complicated. This is the boundary, the open set is spiraling around the surface and is accumulating in this orange set while spiraling. So it's like it's eating away the topology of the surface. So this is the kind of complication that we are thinking of. And the type of result that we expect, in fact, is something like this. Suppose that you have this set here, invariant, for instance. Then we expect that the dynamics in its boundary is going to be pointwise fixed. So it's the simplest possible. There's nothing else. That's the type of result. So in particular, if you have a derived from an also attractor on the torus, and it's invariant by an area-preserving map, it's not an attractor. I'm just talking about the set, not the dynamics. If it is invariant by an area-preserving map, then it has to be fixed point-wise. This is a consequence of the result I'm going to state. Okay. So the reason why, what makes this example, the topology of the boundary of this example complicated, can be explained from the fact that the disk that on the torus is unbounded. It's unbounded in the sense that if you look at it in the universal covering of the surface, in this case R2, then you get an unbounded disk. If you lift it to the universal covering, you get something that goes to infinity in R2. So in general, when you have any surface and you have an unbounded disk, the topology of its boundary is going to have some complication. This is the type of thing that we want to look at. So let's say that the disk, a disk in a surface is bounded if it is bounded in the universal covering. So when you lift it, every component is bounded. So what we want well, if an can an area-preserving map leave invariant an unbounded disk? Of course, because, for instance, the identity, right? The identity leaves invariant anything. But what if we take an example which doesn't have so many fixed points, something more reasonable? For instance, a map with finitely many fixed points. Can we have unbounded invariant disks? And the answer is no, and this is the main lemma, the main result that I want to explain. Is that if you have an area-preserving homeomorphism of a compact surface, which is homotopic to the identity, and its set of fixed points is inessential, and by inessential I mean that that it can be continuously deformed to a point. So it's not the inclusion is homotopically trivial. It is the same as saying that it is contained in some disk. So, for instance, if the set of fixed points is totally disconnected, it is inessential, just to give an example. Well, under these conditions, any invariant disk has to be bounded. So you can't have this type of behavior of disks wrapping around the surface, accumulating. This is for maps homotopic to the identity, but in the case of the torus, we can show the same property for maps in other homotopic classes. For instance, in the then homotopic class, the same thing holds. And in the anosov homotopic class, it's very easy to show that it holds as well. There is a problem that if you consider periodic classes, it's not really true. So, but in general, for maps homotopic to the identity, it always holds. So one of the motivations for studying these invariant disks is the typical picture that one sees when considering area-preserving systems, which is you have invariant islands that appear, and in the complement of the invariant islands, you have a region where supposedly or typically it is expected that the dynamics is interesting. For instance, you see this picture, this kind of picture when you look at the standard family or this family which is analogous but homotopic to the identity. The invariant islands, we know that they appear frequently because of the presence of elliptic points, because of KAM phenomenon. But we want to understand how general is this picture of decomposition into invariant islands and and the complementary region with an interesting dynamics. And also to try to say something about this region in the complement of the invariant islands. And in particular, I want to define this decomposition because it's not clear for a general map how to define the islands and the complementary region. Because, for instance, if you look at the points which belong to an invariant island, this doesn't give a partition of the space. It could be the whole space. For instance, if you take the identity, it's when do we have a decomposition like this, where the complementary, where we have a union of islands, and in the complement we have something interesting. So to understand this better, we will define essential and inessential points. This definition is very similar to a definition used by Tobias Jager to study similar things. In fact, it's equivalent to his definition. So we will say that a point is inessential if it's contained in a periodic open topological disk. And otherwise, it's essential. And so we look at the set of all inessential points, which is clearly an open invariant set. And the complement of this set, we call it C, the set of essential points, which is a closed invariant set. So what I was pointing out before is that the set of inessential points can be an essential subset of the surface. It can be the whole surface, for instance. But when you expect that if this happens, the dynamics has to be very simple, in some sense at least. But in the case that the set of inessential points is inessential, then you can easily see that it has to be a union of disks, a disjoint union of disks. So these disks are what we should call the maximal invariant or periodic islands. They have to be periodic disks if the map is area preserving. And so you have a decomposition. If the set I is inessential, you have a decomposition of the set as a union of periodic disks. And its complement is a fully essential set. A fully essential set is, by definition, precisely that, the complement of a union of disks. It's a set that contains all the homology of the surface or something like that. When you remove it, what remains is a union of disks. So it's a large set in some sense. And then we would like to say, well, first we want to know when can we guarantee that the set of inessential points is in fact inessential. And secondly, we want to say something about the set of essential points, which are the interesting ones, supposedly. So, and the basic idea is that the set of inessential points is going to be inessential whenever the dynamics of F is not reducible in some sense. I will state this in the case of the torus. You can do something similar for higher genus surfaces, but we will do it in the torus, which is an interesting case. So let's say that, so we take the torus as our surface, and we will say that our map F is annular if you can find a direction in R2 so that, and you can find a lift of F to R2, to the universal covering, that has the property that the displacement of orbits using the lift in the direction, in this direction that we fixed, is bounded. So this is what is written there. When you take a point Z and you iterate and you look at the total displacement, it always projected into the V direction remains bounded. So essentially this means that if you take a strip in the V direction, its orbit remains in a strip in the V direction. You can't move away too much in the V, no, in the perpendicular to V. So this is called annular because V is assumed to be here an integer. So it's a rational direction. So we call this annular because essentially you can think of this as the dynamics happening in an annulus. Basically, when this happens, you can show that there is a finite covering of the torus and the lift of F to this finite covering, which has an invariant annulus. So basically, the dynamics is reduced because there appears an invariant annulus. So, okay. And we will say that F is reducible if it has some power which is annular, because essentially the dynamics is not really on the torus, it is happening on the annulus in some sense. Or if there is a power of F which has a very large set of fixed points, a fully essential set of fixed points. Why? Because, well, if you remove the fixed points, what remains is a set in the plane. So it's not really, the dynamics is also not really happening on the torus. And so the theorem is that if you have an area preserving map, homotopic to the identity, and it is irreducible in this sense, then the set of inessential points is inessential. And so you can give this nice description of this nice decomposition of the dynamics. The proof of this is very easy from the bounded disks lemma. I will explain it soon, but before, let me just show a slightly better statement. What we can say when F is irreducible is that the set of essential points is not only a compact connected fully essential set, but it's also weakly transitive. Weakly transitive means that if you take it's the definition of transitivity, but using open sets in the ambient space, right? So, and this is also very easy from the fact, or from the definition and from the bounded disk lemma. So, this is just is beginning to give an idea that the dynamics in this region C is interesting. I will later give a more detailed explanation of the dynamics there. So how do we show this this theorem here? It's very easy, really, because if we are assuming that F is irreducible, then any power of F has an the set of fixed points of any power of F has to be, it can't be fully essential, right? Can't be a fully essential set. So the set of fixed points, there are two possibilities. It is essential or it isn't. If it is essential, the fact that it can't be fully essential implies that it has to contain some component, some connected component, which is like this. But if this happens, this is the set of fixed points, part of the set of fixed points. Well, then clearly the F is going to be annular, because when you go to the universal covering, this becomes something like this, and it is a barrier to the dynamics. Here you have a translation of this. This is a strip which is invariant, and all orbits remain bounded in the transverse direction. So this is precisely what we call being annular. So what this means is that the set of fixed points of any power of F has to be actually inessential. So it must be something like this. It can't contain essential component. But if it is inessential, we can use the bounded disk lemma, which says that there are no unbounded invariant disks. But we can use it for any power of F. So there are no invariant, there are no periodic unbounded disks. So suppose that the set of inessential points is essential. We want to rule this out, right? So if it is essential, then again, it has to contain some it is an open set, right? So if it is essential, this means that it contains an essential loop in the torus. So this loop is contained in the set of inessential point. This means that it is covered. So any point in this loop belongs to some invariant or periodic disk. So you can put it in a disk here. This point is in a disk. There are a bunch of disks covering this loop. Of course, a priori, these disks, the union of these disks, even if you take finitely many, it could be the whole torus. So it could be a union of unbounded disks, or something like that. But the bounded disk lemma says that these disks are bounded. So when we go to the universal covering, this loop becomes something like this. And each of these disks becomes something like this. And of course, there are copies of them covering this whole line. But the key is that since these disks are bounded, in particular, they are bounded in this direction. And since there are finitely many and copies of them, you can put this inside a strip like this. So this is the key, the boundedness of the disks. Because then, all of these disks are, they are periodic actually, right? But we could take we take finitely many, take a power, so they are invariant. So these are invariant disks. Actually, you have to show that they are invariant on the lift as well, but you can do that, choosing a lift appropriately. And then this thing gives an invariant set which separates the plane and remains inside a strip. This, again, implies that F is annular. It bounds the orbits in the transverse direction. So, so the direction V would be this one. But it's not possible because we are assuming that F is irreducible. So it's done. So the key was actually the boundedness of the invariant disks to show that the inessential points are inessential. So how do we show that the set of essential point is weakly transitive? This is also very easy because if you look at an essential point, the essential point here, and you take a small neighborhood of this point and you look at its orbit, then the orbit of this ball has to be an essential set in the torus. Because if it was inessential, the connected component that contains Z would be a disk, or would be contained when you fill some holes, it's going to be a disk. And you can show that this disk is periodic because F is area preserving. But then Z would be inessential because it is contained in a periodic disk. So this is not possible. So the orbit of a neighborhood of an essential point is essential as a set. But you can't have and also the connected component that contains Z is periodic. So you have an essential set which is periodic. So when you look in the torus, you have something like this, for instance. Maybe there are other components, but the connected component of the orbit of this ball that contains Z is essential. But it can't be like this. It can't be just essential in one direction. Because, again, you will have, in this case, you will have a periodic annulus. So this means that if you take a power of F, you have an invariant annulus, and so again, F is annular. And we are assuming that it is irreducible. So this is not possible. So if the orbit of this ball is essential, but it can't be like this, it has to be fully essential, basically. It has to contain a loop, loops in two different directions. Its complement is a union, its complement is contained in disks. But if you have two fully essential sets, it's easy to see that they have to intersect. So when you take 2 points which are essential and you look at their orbits, you get two fully essential sets. They must intersect, and so you get that the orbit of a neighborhood of one point intersects a neighborhood of the other point. So the weak transitivity. And when you assume that the rotation set that your map of the torus has a rotation set with non-empty interior, this theorem can be improved improved a lot. It includes much more information about what happens in the region C. So before stating the result, let me recall some definitions which probably were given by Salvador in his talk yesterday. I wasn't able to come, sorry. If you have a map which is homotopic to the identity in the torus and you take a lift, you can define the rotation vector associated to a point by taking a point in the fiber of this point of the torus. So it's a point on R2. And you look at the displacement after n iterations by the lift, and you take the average. And then you make the limit as n goes to infinity. This is as you do in the circle, right? So this gives like a mean asymptotic displacement of orbits. So the problem is that this limit usually doesn't exist, and even if it exists, it will depend on the point that you chose. But you can show that it exists in many points at least. Well, at least in some points. In fact, there is another definition which is related, which is the mean rotation of a measure. If you take an invariant measure in the torus, then you can define the mean rotation of this measure by a lift of f by integrating the displacement function. So it's how much orbits are displaced on average along the two directions of the torus. The displacement function is simply looking at, you take a point, you take its image, look at the difference, right? How much you traveled. It's induced on the torus by f minus the identity. And so the mean rotation of a measure, it has the following properties. If you take, if your measure is invariant, then for almost every point with respect to this measure, the rotation vector, in the sense that we defined earlier, this rotation vector here, exists for almost every point. And moreover, if the measure is ergodic, then it is equal, the rotation vector of almost every point is equal to the mean rotation of the measure. And if not, then the mean rotation of the measure is the integral of the rotation vectors of the points. This is just a restatement of Birkhoff's theorem. And so you can define the rotation set of a map by looking at the set of all rotation vectors of mean rotations associated to invariant measures. This is, from the definition, obviously a convex set. And in fact, it is not so, it's not obvious at all, but it coincides with the convex hull of the set of all rotation vectors of points. This was proven by Misirevich and Ziemian. And so it's a convex, a compact set, which is also non-empty because we know there are invariant measures. So, okay, so this set, it carries the information of the rotational information of the dynamics, at least on the average. And then when this set has a non-empty interior, you can say many things interesting about the dynamics. First, an observation that since this set is convex and it's compact, it has to either be a point or a segment, or then it has non-empty interior. So when it has non-empty interior, which is of course equivalent to having 3 non-collinear rotation vectors, we know that the map has to have positive topological entropy. We know that there is most of the rotation vectors correspond actually to ergodic measures. So if you take a point, a vector which is in the interior of the rotation set, or a point which is extremal, then it corresponds to an ergodic measure. And moreover, if the vector has rational coordinates, you can take this measure to be Dirac, or an average of Dirac measures. That is, you can take it as you get a periodic orbit, right? If you take a point with rational coordinates in the interior of the rotation set, or an extremal point with rational coordinates, then it corresponds to a periodic orbit. So this means that you have a lot of periodic orbits when the rotation set has an empty interior, because all rationals inside the rotation set correspond to periodic orbits. And moreover, if you take a vector in the interior, which is not necessarily rational coordinates, but anything, then you can find a compact invariant set such that every point in this compact set has that rotation vector. So you have to have a lot of these compact invariant sets, these joint compact invariant sets with different rotations. And so this is a nice example of irreducible dynamics. It's very easy to check that this is irreducible in the sense that we defined earlier. You can't have a very large set of fixed points because it would block rotation on all directions, and you can't be annular for the same reason because you have 3 directions of rotations at least. So this example, for maps with a rotation set with an empty interior, our theorem stated before holds always. One more remark is that this property is typical among area preserving maps. It is generic in any topology. So, for instance, this map has a rotation set with the picture that I showed earlier is a map with a rotation set with an empty interior. So the more precise theorem is that if the rotation set has an empty interior for an area preserving map, then you have this decomposition into the set of inessential points and the set of essential points. The set of inessential points is a disjoint union of periodic disks. These disks are bounded because of the bounded disk lemma. And the set of essential points, the set C, is connected, weakly transitive. It has sensitive dependence on initial conditions. So if you take a neighborhood of a point there, it grows. In fact, it grows a lot. I will explain. And it has positive entropy in this set, inside this set. In fact, to be more precise, you can show that if you take a point which is essential, when you take a neighborhood of this point, you see all the rotational dynamics of F in this neighborhood. You can see all kind of rotation vectors just remaining in this neighborhood. You see points which travel with different velocities in all directions. So this neighborhood has to grow, but it has to grow like the rotation set tells you. Like it's not just in one direction or just a little. And you have a rate of growth also, which is related to the size of the rotation set. And moreover, you can, all these realization theorems that I mentioned earlier, the existence of periodic orbits with a given rotation vector, the existence of compact invariant sets, the existence of ergodic measures, all of these theorems hold inside the set of essential points. So you get a lot of periodic points, for instance, in the set of essential points. There are all kinds of periodic points inside this set. So the dynamics in the set C is really rich in a strong way. Well, this just a remark, this set was studied earlier by Tobias Jager, and he showed the sensitive dependence on initial conditions and some other things, but the problem is that everything after the sensitive dependence on initial condition holds because of the decomposition into bounded islands on the complementary region. And this wasn't known because the key to prove that is the bounded disk lemma precisely. And what allows to realize all periodic points and or invariant measures, etc., in the set of essential points is the fact that the set of essential points is fully essential and its complements is a union of islands. Because what you do is, to prove these things, you use index arguments most of the time. And these index arguments work because you have disks in the complement, so you can compute the index in these disks and make things work. And another observation is that all of these results were also obtained by Salvador Zanata recently in the C1 plus alpha setting. Here we are working with homeomorphisms only, but if the map is regular, then there is a different proof using Pessin theory, and you can conclude all of these things. And moreover, you can prove in this case that the bound on the islands is uniform. So this means that when you take any invariant island or periodic island, its diameter in the universal covering is bound by a uniform constant. In our proof, we can show that it is bounded by a uniform constant if you look at an invariant island. But if you let the period grow, we don't know that the size is uniformly bounded. This, we think it should be true even for homeos, but we don't know. Okay.
Is the map transitive here?
Sorry?
Is the map transitive here?
Strongly transitive. We don't know. Yeah, that's what's missing here. What is true is that, of course, if you show that there are no invariant islands, for instance, you get for free that the map is transitive. Right? And in fact, you can show much more than that. You can show that this is a strong form of transitivity. We did that in a work with Fabio and Nancy Gelman. You can show that if there are no invariant islands, then the dynamics is not only transitive, but it is also transitive in the universal covering. So when you lift to the universal covering, if you choose an appropriate lift, it's transitive. But yeah, in general, we don't know if it has to be transitive in C.
And if it's transitive, you don't know if the periodic wise.
No, also that, we don't know. No. Yeah, I have no idea, but probably Salvador knows more about this. What can you say about the dimension of CF when it is smooth? It's foliated, right? It's laminated by unstable manifolds, or it can it be larger than that? I don't know. Okay, so but usually this set is bad in the sense that it can't be locally connected. At least, yeah, it can't be locally connected. It has to be complicated in some sense. It's fully essential, but it has to do weird things, come and go, because otherwise it will block the dynamics, and you can't have that. Okay, so let me give an idea of how the bounded disk lemma is proved.
Let's say for a typical infinity guy.
Yes?
Would this be all of the terms?
No, because you have usually you will have elliptic islands. Yeah, you have. For a typical C1, then yes. So recall that the boundary disk lemma says that if the fixed points are inessential, then there are no unbounded invariant disks. So the proof is by contradiction, so we assume that there is some unbounded disk. And we will assume that the set of fixed points is actually totally disconnected, not just inessential. This is not too much because, right, an inessential compact set is something like this, something that doesn't contain any, you can put it inside a union of disks, right? So what you can do is you can collapse all the connected components. You have to previously fill them. If they have any holes, you fill the holes and then you collapse them, and then you get a new map which has a totally disconnected set of fixed points. And you have to do some non-trivial work to see that you still have an unbounded invariant disk. Actually, you don't, but you rule this case out in with a different argument. Because it is possible that you have your unbounded disk is something like this, and it keeps crossing the components of the fixed point set. And so when you collapse them, it cuts your disk into pieces which are bounded. So you don't have your contradiction hypothesis any longer. But you can deal with this separately. So we assume that the set of fixed points is totally disconnected. And then the main tool that we use is what we call Brouwer-Le Calvé foliation, which is a foliation with these properties. We put together a recent result of Jolin with the theorem of Le Calvé about the existence of these foliations. And what we obtain is a compact set of fixed points and an isotopy between the identity and F, which fixes this set of fixed points, point-wise, and a foliation in the complement of this set X of fixed points, which is dynamically transverse. Dynamically transverse means the following. If you take a point Z, and you look at the path it follows by the isotopy, so this would be then you can take a leaf of your foliation. What we would like is that the leaf is transverse in this sense, that the path crosses the leaf in a positively transverse way. The foliation is oriented, and we would like the path to cross the leaf from left to right. But this is not necessarily true. It could be like this. However, dynamically transverse means that if this happens, then if you take this path, the path of the isotopy, and you fix the endpoints, there is a map homotopic to this one, fixing the endpoints, which is positively transverse to this leaf. So there is another path here that joins these 2 points without, this path is homotopic to this one without crossing the set X of fixed points, and this one crosses transversely in a positive way from left to right. This has many consequences, dynamical consequences, and I will only state the consequence that we will use about this. So the first thing is that if we go to the universal covering of S, we take the pre-image of X by the projection. We get a set of fixed points in the universal covering. We leave the isotopy between the identity and F, and we get an isotopy in the universal covering, and we get a foliation as well. And this foliation in the universal covering is also dynamically transverse in this sense. And basically, we can assume this. Here I am oversimplifying, but just to get the idea, we can assume that the foliation, the leaves of the foliation join singularities, so points of x. So every leaf of the foliation looks like this. It has two endpoints, which are points of x, like this. So it's a simple foliation. And our unbounded invariant disk has many copies in the universal covering. If we assume that this is not the sphere, if S is the sphere, the theorem is trivial, right? Because everything is bounded. So if S is not the sphere, there are many copies of U in the universal covering, and each copy of U is going to be an invariant unbounded disk, because F is homotopic to the identity, and the lift we took is the appropriate one, so all copies are invariant, and everything is nice. And moreover, each copy has finite area, because it projects injectively to the surface. And so we can define the linking number of a point of x and an open disk. But first, let me give a definition. So if you have a fixed point which is not fixed by the isotopy, and you have a point which belongs to the set x, which is fixed by the isotopy, you can define the linking number between these 2 points by looking following the path of the isotopy for the first point, and looking at how many times it turns around the point which is fixed by the isotopy. Now, if I take an invariant disk instead of a fixed point, I can do a similar definition like this. I take my disk O, and I have a point here which I assume to be outside of O, otherwise I can't do that. This is in X. And then I take any point here, O is invariant. Take any point here, I follow the path of the isotopy, and it will go until F of Z. Of course, it doesn't come back to Z because Z is not fixed, but I can close it in any way I like with a path that remains inside of O, and then I can compute the winding number of this loop around this point. This is independent of the choice of this path and of this point. So this defines a number associated to this disk and this point. So this is what we call the linking number. And so in this definition, the important consequence of the foliation of the fact that the foliation is dynamically transverse is that we can find for any point in the universal covering, we can find a neighborhood V which has the following property. If some disk crosses this neighborhood, then you look at the leaf going through this point, the leaf of the foliation, gamma Z. It joins 2 points, let's say P and Q. Assume these 2 points are outside this disk, and the disk comes close to Z inside the neighborhood V. Then this disk has to link one of these 2 points. This is the main remark. So the linking number between this disk and one of these 2 points is non-zero. This is a consequence of the fact that the foliation is dynamically transverse. And this is very useful because of the following. If we know that this set O contains an element of X, for instance, we know that the elements of X are fixed pointwise by the isotopy. So this point, if you follow the isotopy, remains in place, so it doesn't link this point. Sorry, it doesn't link any of these 2 points, which are outside of U. The isotopy doesn't move. So this means that no point of O is going to link any of these 2 points, because the definition of the linking number of O is independent of the choice of the point. If this point doesn't link anything, then no other point will link anything. So the linking number, if you contain a point of x here, the linking number between O and any point outside is 0. So this means that if O comes close enough to this point Z to intersect the neighborhood V given by the linking lemma, then necessarily one of the endpoints of the leaf through Z has to be inside of O, because otherwise it would have non-zero linking number. And we know this is not possible. So what has to happen is this. So basically, if our set comes close enough to a point, then it eats one of the endpoints of the leaf that goes to this point. And so this is the key to prove the linking lemma, because the boundary of this lemma. One thing is that we can assume that U contains a point of x, basically by choosing x appropriately at the beginning, but in the general case of any surface, not the torus, you have to do some extra work. But anyway, we will assume this. And then to finish the proof, what we do is the following. We know that U is unbounded. If U is unbounded, then you can find a point in the universal covering which is accumulated by infinitely many copies of U. This is easy to see, because U keeps spiraling around, so when you look at the universal covering, it has to cross many fundamental domains, and so using appropriate translations, you get a point which is accumulated by many copies. So you have a point which is accumulating by many copies of U, and they are all disjoint in the universal covering, and they all contain a point of x. In particular, if you take this point, which is accumulated by many copies, well, it has a neighborhood Vz given by the linking lemma, and we can find 3 different copies of U which intersect this neighborhood. So this means, by this lemma, this property which we call engulfing property, that the leaf going through this point has to have one endpoint in U1 and one endpoint in U2 and one endpoint in U3, but this is not possible, right? So this is the contradiction. So this is what finishes the proof. So basically, you can't have many copies of U coming close to a point which is not fixed. And just to finish, let me say that this idea that you can have many copies of U coming close to a point which is not fixed is actually more general. If you take a point which is near this point, you have 3 different invariant sets by an area preserving map, say on the sphere, then it has to be fixed, basically. This is the principle behind this. The same argument more or less works. A simpler statement is this, what we call the triple boundary lemma, and this is a joint work with Patrice Lecalvé and Fabio. We can show that if you take a map of the sphere and you have 3 invariant open disks, then any point which is in the boundary of the 3 disks has to be fixed. The triple boundary point has to be fixed. And for instance, as a consequence, if you have a WADA type continuum, which is this kind of continuum where there are 3 components which the boundary of each one is equal to the boundary of any other component, then if it is invariant by an area preserving map, it has to be fixed pointwise. Well, assuming that the components of the complement are invariant, right? If they are permuted, then it is invariant by an appropriate power of f. And so, for instance, the Plikin attractor has this property, and any hyperbolic attractor in dimension 2 has this type of property, so you will have that if it is invariant by an area preserving map, then it is fixed pointwise. And there are other consequences which are interesting of this idea, and it can be stated in a finer way, but this is still in progress. So I will finish